So moving from our kinetic energy then into some of the examples. How much kinetic energy does a 1 kilogram ball have traveling at 10 meters per second? So as you can guess, it's not really, you're not looking at something that's going to bog you down in terms of algebra. You are just substituting in, making sure the units are correct into the formula. So 100, half of 100, so that's 50 joules of energy. So therefore, the ball has 50 joules of energy. All right. If a curler uses the same amount of energy on an adult stone, 20 kilograms, and a children's stone, 10 kilograms, what's the difference in velocity? Now, this is an example that is very important because we made a connection with delta, the change in energy in the previous one, and I want to point out on this one that it's not going to work out the same for us. So if we go through and find kinetic energy, we don't, we have, 1/2 mv squared. If we went in and we were to look at, they're going to use the same amount of energy here. So let's just call that E for argument's sake. 1/2, and the adult stone is 20 kilograms. We don't know the velocity of the adult stone, so it's going to look like that. If we look at the children's stone, E equals 1/2, mass is 10, and now the children's stone is going to be VC squared. If we do that comparison, if I guess E1 equals E2, just to keep it looking something that you can follow through, then that would mean that 1/2 20 VA squared has to equal 1/2 10 VC squared. The 1/2s would cancel. You divide both sides by 1/2. And if you divide both sides by 10, that inverse operation would cancel out. I would have 2 VA squared equals VC squared. And if we take the square root of both sides, we get that root 2 multiplied by the velocity of the adult stone is equal to the velocity of the children's stone. So therefore, the child's stone is root 2 times faster than the adult stone. All right, that coefficient out front, hey, it's the multiplier. This is how many times faster will it be compared to the adult stone. All right, so it's multiplier. So from that, we get the answer. What would the difference be in velocity? Well, it's the child stone's going root 2. So root 2 is approximately, you can do, it doesn't matter to me, you can do decimals. Well, it's about 1.7 times faster. All right. So this is the one that shows that, we'll talk about delta energy, or change in energy for a second. So kinetic energy, 100 kilogram person, how much do they have if they run at 4 meters per second? So kinetic energy equals 1/2 mv squared. So 1/2 times 100 times 4 squared. So this is how much energy they have if they run at 4 meters per second squared. And we get 800 joules. Therefore, 800 joules at 4 meters per second. B part. What happens when they change velocity? What happens if they drop down or slow down? So they've changed velocity from 4 to 2, so they've gone to half the velocity. So if we do the calculation for that, what you're going to find is that 0.5 times 100 times 4 is 200 joules. Half the velocity is not half the energy. So therefore, 200 joules at 2 meters per second. Okay. So see, why is the relationship not linear if it was half the height, it was half the energy back with the potential. Why for kinetic is it not? Well, let's do an analysis here of delta EK. So that would be EK1 minus EK2. So that change in energy is 1/2 m v1 squared minus 1/2 m v2 squared. So still have common factors here. We have the 1/2 m we can pull out. So 1/2 m, and we're left with v1 squared minus v2 squared. And it's not a linear relationship. It's not a one-to-one relationship. This is actually a quadratic relationship. So we have a quadratic relationship, which means that we can't simply write it as delta V. Okay, that's as far as we can actually take it. So you can add this formula on to your formula sheet. It's not necessary. The important thing is to realize that V1 squared minus V2 squared is not equal to delta V squared. All right, and I'll put this down here. So V1 squared minus V2 squared does not equal delta V squared. Okay? All right, so very, very important. So that change in energy, it's not linear because it's a quadratic relationship where it's it forms a parabola of the velocity, so they don't have that nice one-to-one or linear relationship. So delta V cannot be calculated simply by going 4 minus 2. Okay, so be aware of that, please, and make sure you have the appropriate, and make sure it's clearly marked that this is change in kinetic energy, this formula here. Okay, that's it. That allows you to do a bunch of homework, mixture of gravitational potential and kinetic energies. If you have any questions with them, for the most part, they're going to be straightforward. You do, again, be comfortable with working with mass not being known. It's not necessary to have numbers all the time for everything. And other than that, everything should go all right. So if you have any questions, please let me know in class and we will get them cleared up as soon as we can.